Hello there, and welcome to the Late Night Scientist channel. In this calm journey through deep time, we'll follow the evolution of flowers and the colors they carry, how pigments first emerged as quiet tools of survival, how insects shaped the language of petals, and how entire landscapes were painted by climate, chance, and adaptation. From the world's first modest blossoms to the vibrant blooms shaped by human hands. This is the story of how beauty became a strategy, and how every petal today holds the memory of life's ancient experiments. Let your mind drift as we explore color not as decoration, but as the history of survival written across the living world. The story of flowers begins far earlier than petals, and far earlier than any creature bothering to ask, "How do I look?" It begins in a world where nothing is trying to be noticed, and nothing yet has the luxury of being admired. Picture Earth more than 1 billion years ago, an oceanic planet glinting under a young, temperamental sun. The land is barren, save perhaps for a few stubborn microbial crusts gripping ancient rock. Wind lashes across empty shorelines. Water carries nutrients, chemistry, and possibility, but not color in the way we think of it. Not yet. This world is tinted mostly in quiet, natural tones. Deep marine blues, earthy minerals, scattered browns where sediment collects. The life that exists belongs to the tiniest of pioneers, microbes drifting in the ocean, forming films, mats, colonies. These early organisms are not concerned with being beautiful or expressive. Their use of color is purely functional, as practical as a tool placed in a toolbox. To them, a pigment is not an invitation. It is a shield, a sponge, a quiet survival mechanism. Under the bright, often harsh radiation of the ancient sun, pigments evolve as a kind of biological umbrella. Some molecules absorb harmful wavelengths, preventing DNA from unraveling under ultraviolet exposure. Others capture specific bands of light to power primitive forms of photosynthesis. In these early oceans, color behaves almost like a secret language, but a language spoken inward, not outward. It is chemistry talking to itself, not yet part of an ecological dialogue. If we could drift quietly above one of these early microbial mats, perhaps perched on a gentle current, we might see subtle hints of reds and purples, far from the vivid shades that flowers will someday flaunt, but present nonetheless. These colors come from pigments like bacteriorhodopsin, primitive molecules that help early life convert sunlight into usable energy. To human eyes, they appear faint, almost shy, as though the world is merely warming up before performing its symphony of hues. In these ancient seas, no creatures have eyes. Not eyes for color, certainly. The very idea of seeing is still eons away. Color, at this stage, is entirely one-sided. It exists without audience, without intention, without meaning beyond the immediate survival of the cell that contains it. Even the deep greens we associate with life are not yet widespread. Chlorophyll, the iconic pigment of plants, is a later innovation. For now, early Earth leans toward earthy browns and muted pinks, like a world painted with a brush that someone rinsed a little too thoroughly. Far above, the sky itself is different, a bit hazier, veiled with volcanic gases and dust, shifting between pale blues and milky grays. The atmosphere is still learning how to balance itself, trading gases like a young merchant discovering the rhythms of commerce. Oxygen is only beginning to accumulate. The world feels quiet, almost contemplative, as if lingering in a long inhale before the exhale that will bring complex life. The continents, still rough-skinned and unsettled, display little more than bare rock. No forests soften their edges. No grasses ripple under the wind. No flowers brighten a landscape still waiting for its invitation to bloom. If a viewer from the distant future were dropped here, they might assume Earth was still deciding whether to support life at all. But life is here, humble, small, hard-working, and persistent. It clings to surfaces, floats in water, spreads in slow sheets where conditions allow. In these vast microbial communities, subtle patterns emerge, spreading rings, branching filaments, delicate layers. These patterns are not created for beauty, yet they hold a quiet charm, like the accidental swirls in a potter's clay. Evolution, still early in its experimentation, has no interest in aesthetics. It is concerned with what works, what survives, what allows a cell to divide and try again. Yet even here, in this subdued world, the seeds, metaphorical ones, of future beauty are being planted. Pigments evolve new tasks. Some buffer oxidative stress. Others stabilize membranes. Some act as tiny molecular shields. Color becomes deeply intertwined with survival, layered into the basic chemistry of life. None of these pigments intend to announce anything to anyone, but they will eventually become the foundational palette for every wildflower meadow, every tropical forest, every garden cultivated by human hands. It's almost comical to think that these early molecules, invented strictly for practicality, will one day be admired, romanticized, and carefully bred into countless varieties. But for now, they work in solitude, blissfully unaware that future creatures will someday swoon over their descendants. In this world before petals and before intention, color exists without storytelling. It is simply a tool. But like many tools evolution discovers, it will someday be repurposed, reshaped, and reinvented. Color will transform from a quiet chemical necessity into a vibrant ecological conversation. But for the moment, in this first chapter of Earth's long saga, it remains humble, working backstage, preparing the world for a performance still millions of years away. The moment plants stepped onto land, figuratively of course, since plants aren't known for dramatic entrances, Earth entered a new evolutionary chapter. Before this transition, life had been largely carried by water. The ocean handled everything: support, transport, nutrients, protection. It was like living in a world with built-in room service. And then gradually, some pioneering algae began to explore shallow edges, testing out the idea that maybe life could exist on land too. It was a bold notion for creatures that lacked legs, plans, or any sense of real estate value. Land, at first, offered little comfort. It was rough, dry, and unforgiving. an environment where every step toward survival required innovation. But what early plants lacked in mobility, they made up for in patience. Slowly, so slowly that geological clocks barely noticed, they adapted. Roots dug into the ground, anchoring them against wind and gravity. These primitive roots didn't think grand architectural thoughts. They simply held on, absorbing what moisture they could. In doing so, plants accepted the first of many limitations. Once rooted, they could no longer go anywhere. Immobility might seem like a disadvantage. Most animals would certainly complain if told to spend life bolted to the floor. But plants leaned into the idea. They developed bodies suited for stillness. Stems lifted them toward sunlight. Leaves unfolded like cautious hands, trying to catch every photon the air offered. Bit by bit, plants reshaped themselves into organisms perfectly designed to stay put. Yet with this new lifestyle came a challenge that evolution had never encountered in quite this way: reproduction without movement. In water, reproductive cells drifted easily, carried along by currents. But on land, fertilization became a problem of logistics. How could two organisms who never moved exchange genetic material across dry, open ground? Early plants solved this problem with the simplest strategy available: release spores and hope. Hope they traveled far enough. Hope they landed somewhere moist. Hope they didn't end up in a patch of sun too bright for comfort. Spores were incredibly light, designed not for accuracy, but for abundance. The air filled with them during certain times, like tiny travelers without maps or destination. They floated wherever the wind carried them, navigating the world with all the precision of pollen in a spring breeze, which is to say, none. If modern plants sometimes rely on luck, ancient plants relied on luck's more unpredictable cousin, chance dressed in determination. This was a world still without expressive color. Early land plants weren't trying to stand out. They had no reason to be visible, because nothing had eyes capable of appreciating them, nor did they have any messages to send. Their structures were plain, their surfaces simple, their tones mostly muted greens and browns created by basic pigments doing their usual survival tasks. These plants were not competing for attention. They were competing for stability, moisture, and just enough sunlight to carry out their daily chemical responsibilities. Wind became an essential collaborator in reproduction, even if it was occasionally unreliable. When the air currents favored them, spores could travel incredible distances. When the air was still, spores simply collected near their parent plant in quiet little piles, waiting for a shift. This was the earliest form of propagation via atmospheric cooperation, plants releasing tiny packets of hope and then politely waiting for nature to get around to its part. One could imagine an ancient plant murmuring, "Any day now," while a breeze considered drifting elsewhere. Even as plants spread slowly across the landscape, they transformed the land itself. Their presence stabilized soils, reducing erosion. Their roots, however modest, held sediment in place. Their bodies trapped moisture in shaded pockets, subtly shaping the early terrestrial environment. They didn't intend to engineer the world. They simply did so by existing. Stillness can be surprisingly influential when practiced at continental scale. As plants grew taller, they encountered a new challenge: supporting their own weight. In water, buoyancy had been a comfort. On land, gravity had opinions. This led to sturdier tissues and structures capable of lifting leaves toward the sun. These innovations were purely mechanical, designed to resist collapse. There were no flowers, no ornamentation, no visual experiments. Everything was shaped by necessity. The earliest forests were humble, low-lying expanses of plant life that hugged the ground or rose only slightly above it. The world was still waiting for grandeur. Yet even in this simplicity, something important was happening. By anchoring themselves and embracing immobility, plants created the conditions necessary for future innovation. Choosing to remain still forced evolution to explore alternatives: chemical signals, airborne particles, new structural strategies, and eventually, entirely new methods of communication. The journey toward flowers began not with beauty, but with stillness. Not with color, but with commitment to place. Plants became masters of the long game. They learned to survive by waiting. Waiting for rain, waiting for sunlight, waiting for the right gust to carry their spores into the next hospitable patch of earth. Their patience was not passive, it was strategic. They turned time itself into a tool, letting the world move around them while they persisted. Someday, long after spores ruled the air and quiet green forms ruled the land, plants would begin experimenting with ways to be noticed. They'd learn to signal, to attract, to communicate through color and form. But that comes later. For now, in this early stage of terrestrial life, plants simply endure, rooted, quiet, and hopeful, trusting the wind to deliver their future. Green did not conquer the world through charisma. It didn't stroll onto the evolutionary stage with confidence or flair, nor did it audition for the role of Earth's signature color. Green simply worked. And in evolution, what works tends to stick around. Chlorophyll, the pigment responsible for much of the green we see today, wasn't invented as decoration. It was invented as a biochemical tool. The kind of tool that quietly revolutionizes everything without anyone appreciating the elegance of its engineering. To understand why green became the planet's dominant shade, imagine the sun not as a warm, friendly disk in the sky, but as a generous yet demanding provider of energy. Plants needed a way to capture that energy and convert it into something usable. Food, growth, structure, the building blocks of living tissue. Chlorophyll answered that need by absorbing specific wavelengths of light, especially those rich in energy, red and blue. What it didn't absorb, what it more or less shrugged off, was green. And so, like a painter splashing leftover color across a canvas, the world became covered in the very wavelengths life happened to ignore. This reflects a simple truth about nature. It doesn't aim for beauty, but beauty often shows up anyway. Chlorophyll's green glow is the result of pure practicality. The pigment's molecular structure is tuned to harness photons efficiently using their energy to power photosynthesis. It has no interest in our aesthetic preferences. If plants could speak, they might defensively insist, "We're not trying to be pretty, we're trying to survive." Anything else is incidental. Early terrestrial landscapes transformed dramatically under the spread of chlorophyll-rich plants. What had once been a patchwork of bare, rocky terrain slowly shifted into a tapestry of verdant tones. Greens spread across wetlands first, then along riverbanks, then up slopes where moisture was still reliable. As plants reached upward and outward, a subtle but profound change unfolded. Earth began to wear a living coat. But this coat, for all its beauty in hindsight, was visually monotonous. Different shades of green, certainly, some darker, some brighter, some with hints of blue or yellow, but all united by the same central pigment doing the same essential task. Forests, once they arrived, were overwhelmingly uniform in coloration. Meadows shimmered with movement, but not with variety. It was a world rich in life yet restrained in palette, as if nature were still warming up its brush before attempting more daring strokes. Green's dominance also shaped the experience of all other organisms. Animals evolving later would learn to navigate environments saturated with this hue. Green became the backdrop for survival, the camouflage for some, the contrast for others, the ever-present setting for predator and prey alike. For countless species, blending into a green world became an evolutionary necessity. Many insects learned the trick early, adopting leafy hues that rendered them nearly invisible. Birds developed feathers that either merged with the foliage or stood out strikingly against it, depending on their needs. Green was the constant against which every other color learned its meaning. Chlorophyll itself is a remarkable molecule, intricate yet durable. At its core lies magnesium, anchored by a ring of carbon and nitrogen, a structure efficient enough that it has endured for hundreds of millions of years with only minor variations. Evolution rarely leaves a good invention untouched, and chlorophyll has undergone refinements. But the basic blueprint has remained astonishingly consistent. If nature had a favorite tool on its workbench, this would be it. Dependable, adaptable, and endlessly useful. Despite its dominance, chlorophyll did not eliminate the existence of other pigments. Plants produced additional molecules for protection, structural support, and metabolic balance. But in this chapter of Earth's history, those pigments stayed mostly hidden. They were understudies waiting for their moment, concealed behind the powerful curtain of green. Only in certain conditions, such as drought, cold, or nutrient scarcity, would these other colors briefly surface, revealing reds, yellows, and purples that hinted at the vibrancy plants were capable of. Yet these flashes were temporary, mere glimpses of a drama still millions of years from unfolding. One might imagine green becoming the default mode for plants. Not fashionable, not flashy, just universally functional. It coated leaves, stems, and even early forest floors. When the wind shivered through ancient vegetation, it stirred waves of green stretching to every horizon. There was beauty in the uniformity, though few organisms existed to appreciate it. Green may not have asked for applause, but it earned a quiet admiration from the life that depended on it. if only in the way a creature instinctively seeks shade, oxygen, or a patch of foliage sturdy enough to rest upon. Even as plants experimented with new shapes, heights, and growth patterns, the color remained stable. Green was the shared language of photosynthesis, the visual signature of life making its living directly from sunlight. And for millions of years, that was enough. Flowers had not yet evolved to flaunt brighter hues. Fruits had not yet ripened into reds and oranges to tempt hungry animals. The world was not yet decorated. It was simply functioning. In the long, steady march of evolution, chlorophyll set the stage for everything to come. It powered forests, fed ecosystems, and stabilized landscapes. By being so efficient, it allowed life to spread far and wide. But in doing so, it also imposed a certain visual quiet across the planet, a softly whispered beginning to the story of color. Someday, plants would learn to use pigments for more than survival. They would discover communication, attraction, strategy, and spectacle. But for now, green reigned alone, not because it tried to, but because it never needed to try at all. Long before petals began competing for admiration, and long before animals evolved eyes capable of appreciating them, plants were quietly conducting experiments in chemistry. These experiments had nothing to do with beauty. They were not rehearsals for the botanical spectacle that would arrive later. They were survival strategies, practical, reactive, often improvised solutions to environmental stress. Yet from these biochemical maneuvers emerged the very pigments that would one day paint the world. To understand this early chapter in color's history, imagine a world still dominated by the greens of chlorophyll, but studded with occasional accidental accents. Purple shadows where leaves struggled against cold, golden tones where tissues concentrated protective molecules, muted reds in fruits that were not yet trying to advertise ripeness. These were not displays. They were symptoms of adaptation. The first pigments outside of chlorophyll served as tiny chemical shields and buffers. Carotenoids, for instance, appeared early as molecular bodyguards. They absorbed harmful wavelengths of light and protected plant tissues from oxidative stress. In essence, they acted like a sunscreen applied from within, blocking the sun's harsher elements while letting just enough energy pass through for chlorophyll to do its work. The yellows and oranges these pigments produced were never meant to be seen. They simply existed because the molecules forming them were good at their jobs. Anthocyanins, responsible for reds, purples, and blues, played a different role. These pigments formed in response to cold, drought, and nutrient scarcity, acting as a kind of biochemical insulation. When temperatures dropped, some leaves produced anthocyanins to reduce light stress and prevent cellular damage. This resulted in a faint blush creeping across plant surfaces, not out of embarrassment, but out of necessity. It is somewhat charming to imagine a leaf flushing purple because it feels chilly, even though the chemistry is far more practical than emotional. These early pigments also acted as antioxidants, neutralizing reactive molecules created by environmental stress. In drought, for example, anthocyanins accumulated to help stabilize plant tissues. The color shift, however subtle, signaled that the plant was under duress, but only to those who could interpret chemistry rather than sight. Since no animals yet existed to witness the transformation, the color was less a warning sign and more a quiet internal adaptation. Fruits, long before they became colorful invitations to animals, also developed pigment changes tied to stress. A fruit darkening under strain wasn't trying to advertise readiness. It was coping. As tissues matured or encountered challenging conditions, pigments shifted to protect cellular structures. It's a bit poetic in a way that these early fruits grew deep hues under pressure, nature's version of a bruise, but one that reinforced rather than weakened the organism. None of this early color existed for communication. There were no eyes to receive messages, no interactions shaped by visual cues. The world at this stage simply wasn't listening to color, nor was color trying to speak. These pigments were tools, not art. They were the equivalent of insulation tucked behind walls, functional, vital, and completely unconcerned with how they looked. Yet, despite their purely practical origins, pigments quietly laid the groundwork for future evolutionary leaps. At a molecular level, these compounds introduced flexibility. With carotenoids and anthocyanins already present in plant biochemistry, evolution later found opportunities to repurpose them. What was once purely defensive could become expressive. What began as internal shielding could one day serve as external signaling. But these transformations would come far later. In this era, pigments remained tucked away like underused instruments, playing faint notes only when the environment demanded it. Color, at this point, belonged to stress. A leaf might redden at dawn, not because it wanted attention, but because the cool morning light created conditions that favored anthocyanin production. Some plants developed permanent tints, bronze, burgundy, or dusty violet, because these pigments offered a consistent advantage in their habitats. These hues blended into the environment rather than disrupting it, lending the world a subdued variety, a gentle shift away from uniformity. The landscape began to change. Valleys filled with plants carrying traces of these pigments might appear subtly warmer at the edges. Rocky outcrops dotted with hardy species could display deeper tones, hinting at the resilience hidden within their cells. This emerging complexity added quiet richness to terrestrial ecosystems. Not bright, not bold, just more varied than before. Carotenoids also played a surprising role in stabilizing photosynthesis itself. They acted as safety valves, capturing excess light energy and releasing it harmlessly. Without them, chlorophyll could suffer damage during sudden shifts in sunlight. This meant plants could survive in brighter, more exposed areas than ever before. Over time, ecosystems expanded into zones where photosynthetic life had once struggled. Carotenoids were not just pigments. They were permission slips, allowing plants to explore new environments. Anthocyanins, too, increased ecological resilience. Plants with the ability to produce them could tolerate a wider range of conditions: colder mornings, brighter afternoons, nutrient-poor soils. These pigments were survival multipliers, enabling growth in habitats that would otherwise remain barren. In these subtle expansions, the world grew more textured, more stable, more prepared for the burst of complexity that lay ahead. If evolution had a sense of humor, and sometimes it feels like it does. It might smile at how these pigments, invented for quiet biochemical chores, would eventually become stars of botanical art. The purples created to shield a stressed plant would someday become colors prized by gardeners. The carotenoid yellows that protected tissues from light damage would eventually brighten meadows. But in this chapter of Earth's story, their purpose was humble. Color existed, but no one admired it. Pigments worked, unseen and uncelebrated. And in doing so, they prepared the world for a future where colors would finally step from behind the curtain and speak openly to the living world. In the long, wandering story of plant evolution, few innovations altered the rhythm of life as dramatically as the invention of seeds. Before seeds existed, plants relied mostly on spores, tiny, weightless packets of potential flung into the air like hopeful confetti. Spores traveled wherever the wind sent them, with all the precision of a message in a bottle tossed into the ocean. Success depended on chance. Land in a moist crevice, germinate quickly, and avoid becoming lunch for whatever small creature might stumble across you. It worked, just barely, but it was neither efficient nor predictable. Seeds changed that. Seeds were not accidents on the breeze. They were deliberate. A seed packaged nourishment, protection, and genetic material inside a single structure capable of withstanding dryness, cold, hunger, and time itself. Compared to spores, seeds were fortresses. They were vaults of possibility. A seed could wait, lingering through droughts or winters or geological pauses until conditions finally whispered, "Now." If spores lived in the moment, seeds lived in anticipation. To early seed-producing plants, this innovation must have felt like discovering the concept of planning. Suddenly, reproduction no longer needed to be a frantic, scattershot affair. Seeds allowed plants to place their offspring with care, placing them not just in space but in time. A seed that landed in poor soil could bide its moment. A seed caught in a quiet hollow could rest there until rainfall returned. A seed frozen beneath seasonal snows could emerge when warmth crept back into the world. In a landscape still prone to extremes, this waiting game was invaluable. Structurally, seeds were marvels of biological engineering. Each one was a tiny package containing an embryo, a supply of food, and a protective coat. The food, often starches or oils, served as the starting capital for new life, giving seedlings a crucial advantage over their spore-borne ancestors. Instead of scrambling immediately to find nutrients, a sprouting seedling could ease into existence, drawing from its stored reserves like a traveler carrying rations across uncertain terrain. This storage ability opened the door for plants to grow in environments previously too unpredictable for spore-based life. Seeds could withstand dry seasons, intense sunlight, or frosty nights that would have spelled doom for delicate spores. Entire ecosystems shifted as seed plants spread into new regions, gaining a foothold in landscapes where their ancestors would have faltered. But the true power of seeds wasn't just endurance, it was opportunity. Seeds created a new interface between plants and the wider world, inviting forms of partnership unknown in earlier eras. As seeds became more complex, They developed protective coverings, shells, husks, coats, that varied in thickness and structure. Some seeds evolved to open only under certain conditions, such as after fire or extreme drying. Others developed mechanisms that favored specific dispersal strategies, hooks for clinging to fur, wings for catching the wind, buoyant shells for floating along waterways. These adaptations weren't random flourishes. They were quiet attempts at collaboration. One could imagine an ancient plant observing its seeds traveling farther when they latched onto the fur of passing creatures. The plant itself did not think, of course, but evolution did what it always does. It nudged successful traits forward. Seeds became more enticing, more transportable, more strategically shaped. In a sense, plants began recruiting couriers, unaware couriers but effective ones, with every animal that brushed against them. And while flowers had not yet entered the scene, seeds already laid the foundation for future communication. For the first time, plants developed traits meant to influence the behavior of other organisms, even if unintentionally. A shell that resisted digestion encouraged animals to carry seeds longer before depositing them elsewhere. A structure that tasted mildly appealing ensured the seed would be eaten but not destroyed. These were the earliest whispers of a new evolutionary language, a plant influencing an animal's behavior through structure alone. Seeds also opened doors to complexity within plant communities. With improved survival rates and more reliable dispersal, plants could diversify more readily. They could afford to experiment, to modify leaf shapes, to alter growth habits, to explore multiple strategies for occupying the same ecological space. Diversity blossomed, even though flowers had not yet evolved to express it in color. The world began to feel more layered, more structured, more capable of supporting intricate webs of life. One of the quietest miracles of seeds was dormancy. A seed could remain inactive for months, years, sometimes centuries, holding life in suspension. In this paused state, the seed endured storms, floods, fires, and the slow working of geological time. It did not panic. It simply waited. Seeds, in their serene resilience, embodied a kind of botanical patience unmatched by most forms of life. If spores were fleeting, seeds were steadfast. Tiny, steadfast optimists wrapped in hardened shells. This patience reshaped ecosystems. Fires that once wiped out vegetation now triggered germination. Seasonal cycles that once dictated strict timelines now offered windows of opportunity. Even inhospitable soils became potential nurseries once seeds arrived, ready to sprout at the faintest hint of moisture. Landscapes began to teem with plants that grew not because the moment was perfect, but because seeds had lingered long enough to take advantage of the smallest openings. Though the age of flowers was still far ahead, seeds quietly prepared the world for it. They created longer lifespans, wider ranges, richer habitats, and more complex relationships among plants and animals. They laid the groundwork for color, not simply through pigments, but through the partnerships they made possible. Seeds were the first plant parts to truly invite others into the story. Later, plants would add scent, shape, and color to attract collaborators more intentionally. But seeds were the first step in that direction. They were survival plans wrapped in optimism, carried through landscapes by wind, water, accident, and eventually willing participants. With seeds, plants didn't just spread, they strategized, and the world, without realizing it, began preparing for the coming bloom. Long before wild meadows shimmered with color, before gardens unfurled like living paintings, before petals even dreamed of elegance, the very first flowers appeared. They were not the showpieces we picture today. They were discreet, minuscule, and utterly unglamorous. Quiet problem solvers tucked into the greenery of ancient landscapes. If one could travel back to this early world and search for flowers, it would take patience, perhaps a magnifying glass, and a sense of humor. The first blossoms did not announce themselves. They barely whispered. These ancestral flowers emerged during a time when seed plants already existed, but faced persistent challenges. How to protect delicate reproductive structures, how to transport pollen more accurately, and how to increase the chances of producing viable seeds. Cones, used by earlier plants, were sturdy but limited. They relied heavily on wind, a partner that was famously inconsistent and rarely precise. Early seed plants needed a new strategy, something more refined and adaptable. And so, gradually, the first flowers took shape. They did not begin with the intention of being colorful or ornate. Their earliest forms were compact and functional, resembling tiny clusters or simple arrangements of modified leaves surrounding reproductive organs. These structures weren't petals in the aesthetic sense we know today. They were protective shields, guiding surfaces, and structural supports. A flower, at its core, was an innovation to improve efficiency, nothing more, nothing less. In those first experiments, petals were small and often dull. They likely shared the same earthy tones as the surrounding foliage. Their purpose wasn't to stand out. It was to ensure that pollen reached the right place at the right time. If ancient flowers had consciousness, they might have politely insisted, "Please don't mind me, I'm just working," and then immediately gotten back to their microscopic business. The world these early flowers inhabited was turning more complex. Forests and understories offered countless microhabitats where subtle advantages mattered. A plant that produced a more enclosed reproductive structure could shield its pollen from rain or wind too strong for delicate grains. A plant that shaped these structures inward could better control the exact arrangement of pollen-producing parts and pollen-receiving parts. Small architectural tweaks had significant consequences, and so, even without intending to create beauty, early flowers became intricate. Their anatomy evolved toward specialization. Enclosing the ovules within carpels created protection from drying and predators. Developing stamens that released pollen in controlled bursts increased reproductive reliability. Layers of modified leaves began arranging themselves around these reproductive centers, forming the earliest variations of perianths, the forerunners of petals and sepals. These designs weren't expressive. They were mechanical improvements, like reinforcing the frame of a house or angling a door so it shuts more easily. What these early structures did, intentionally or not, was create a stage where future visual signaling could eventually emerge. But at this moment in evolutionary time, the actors were shy, small, and decidedly uninterested in applause. These proto-flowers also played a subtle role in microclimate control. Their enclosed structures could maintain a delicate internal environment, slightly more stable than the world outside, preserving humidity, regulating exposure, even reducing the risk of pollen clumping. These internal sanctuaries supported more effective fertilization. The earliest flowers didn't attract anything. They simply created better conditions for themselves. Yet even in their modesty, they hinted at a future of lavish diversity. By forming a contained reproductive chamber, they opened the door to selective refinements on a scale earlier plants had never explored. Tiny changes in shape began directing how pollen moved within the flower. Slight differences in texture or arrangement influenced how easily pollen detached or adhered. Gradually, flowers became miniature laboratories, experimenting silently with structural opportunities. During this early stage, insects were present in the world, but their interactions with flowers were still accidental. A small beetle might stumble over a flower and pick up pollen grains by sheer clumsiness. A primitive wasp might brush against a floral surface without realizing it was participating in the earliest steps of a partnership that would one day reshape the planet. These meetings weren't yet coevolution. They were coincidences. But coincidences evolution sometimes likes to explore. Still, the first flowers did not design themselves with insects in mind. They were not enticing. They were not fragrant. They were not adorned with ultraviolet patterns or vibrant hues. If anything, they behaved like introverts at a gathering, present, functional, and quietly hoping nobody would make a fuss about them. One of the remarkable things about these early flowers was their scale. Many were no larger than the tip of a fingernail, some even smaller. They nestled within leaves or emerged in clusters barely noticeable against the plant body. Their small size was not a failure of ambition. It was effective. Larger structures would have required more resources without offering any advantage at this stage. Miniature precision was far more efficient. As flowering plants continued to refine this new reproductive strategy, they unlocked a versatility unmatched by previous plant lineages. Flowers could adjust their shapes to fit their environments. They could cluster densely or remain solitary. They could orient themselves upward, downward, sideways, whatever position best protected their pollen. This adaptability, even before beauty arrived, made flowering plants an evolutionary force with potential. The earliest flowers, unimpressive though they were, marked a quiet turning point in Earth's history. They introduced a modular system of reproduction, one that would eventually combine genetics, structure, and environment into a dynamic interplay. They were small innovations that rewrote the rules of plant life. And while they would someday evolve into brilliant shapes and styles that attract animals and humans alike, their beginnings were as humble as a tool forged for practicality. If these ancient blossoms could hear the praise showered upon their descendants today, they might feel embarrassed by the attention. After all, they never meant to start a global fashion revolution. They simply meant to improve fertilization. No need for admiration, and certainly no need for staring. When insects first wandered into the world of flowers, it was not with the poetic elegance we might imagine today. There were no graceful landings, no delicate sipping of nectar, no shimmering wings politely dusted with pollen grains. The earliest encounters were far less coordinated, a mix of bumbling steps, accidental smears, and mutual confusion. Yet from these awkward exchanges emerged one of the most transformative collaborations in the history of life. At this time, flowers were still modest structures focused on internal organization rather than external allure. But insects, especially small beetles and primitive flies, presented an unexpected opportunity. These creatures were constantly searching for food, shelter, or simply something interesting to walk on. And flowers, with their sheltered pockets and occasional traces of nutrient-rich materials, provided just that. Some insects crawled into flowers looking for warmth. Others explored out of curiosity. A few nibbled on pollen, not knowing they were carrying the future of botanical communication on their legs. The magic of this early partnership wasn't in grand design. It was in the subtle realization that when insects visited flowers, pollen moved more reliably. Wind had always been a fickle courier, but insects, even when clumsy, were at least targeted. They traveled from plant to plant, following their own needs rather than the whims of the weather. A flower brushed by an insect was more likely to achieve fertilization, and evolution took note. So flowers began experimenting. The earliest experiments were small, almost unnoticeable. A slight shift in pigmentation here, a faint chemical scent there. These changes were not meant to attract. They simply altered the flower's microenvironment, cooling it, warming it, protecting delicate tissues. But insects, with their sensitive antennae and developing sensory abilities, began responding to these differences. A flower with a faintly sweet chemical signal might receive a bit more attention. A bloom with a slightly brighter tone might catch the faint glimmer of an insect's compound eye. The interactions were subtle, but they nudged both sides in new directions. Over time, these nudges accumulated into patterns. Flowers that produced mild scents, originally internal cues that leaked into the air, began inadvertently signaling their presence. Insects followed these cues, not out of loyalty, but because the flowers contained small nutritional rewards. In turn, flowers that offered these rewards gained a reproductive advantage, and so the cycle deepened. The stage was set for co-evolution, though both participants behaved less like enthusiastic partners and more like neighbors gradually learning to share a fence. The emergence of color variation played a quiet but profound role. Early pigments that once served only as stress responses now became tools for visibility. Flowers weren't producing bold hues yet, but they began shifting towards subtle contrasts, slightly lighter centers, slightly darker edges, faint lines guiding inward. These weren't displays of beauty. They were functional innovations to help insects navigate tiny, complex floral spaces. A flower that guided an insect more efficiently wasted less pollen and improved its odds of fertilization. Meanwhile, insects themselves were evolving new sensory adaptations. Their vision grew more refined, allowing them to distinguish shapes, brightness, and eventually wavelengths beyond what humans would later see. Their behaviors became more predictable. Some insects started visiting certain flower types repeatedly, learning which shapes or scents consistently provided reward. These early preferences were primitive, but they set the groundwork for later specialization. This partnership had an unexpected consequence: structural innovation. As insects moved across flowers, they inadvertently selected for shapes that facilitated pollen transfer. Some flowers began developing landing platforms. Others tightened their structures so only particular insects could enter. A few early lineages experimented with concealed pollen, ensuring that only persistent or appropriately sized visitors could reach the reproductive organs. It was less about exclusivity and more about quality control, flowers minimizing wasted effort by quietly shaping their clientele. On the insect's side, mouthparts evolved gradually toward more efficient feeding on liquids or fine particles. Antennae became better at detecting fragrance molecules drifting through the air. Even behavior shifted. Insects that lingered slightly longer inside flowers, brushing against reproductive surfaces, unintentionally became better pollinators. None of this arose from desire. It was simply evolutionary economics. An insect that found reliable food sources survived better, and a flower that used insects effectively reproduced more. Though this relationship would eventually give rise to spectacular coevolution, bees with specialized pollen baskets, flowers with ultraviolet maps, nectar wells designed for specific tongues, its beginnings were grounded in simplicity. Just two types of organisms trying to navigate their respective lives, incidentally improving each other's success. Perhaps the most charming part of this era is how unromantic it truly was. No evolutionary love stories, no conscious collaborations, no sweeping gestures of attraction. Just a slow, practical negotiation between flowers that needed pollinators and insects that needed nourishment. If this were a romance, it would be one where both characters agree to meet every week out of convenience and gradually discover that the arrangement works surprisingly well. As this quiet partnership deepened, the world changed. Pollination became more reliable. Reproductive success increased. Flowering plants diversified faster than other groups, exploring shapes, scents, and subtle colors. Insects diversified alongside them, learning to exploit these new opportunities. Together, they formed one of nature's great mutualisms, fundamentally altering ecosystems and paving the way for the explosion of floral color yet to come. But in this chapter, the relationship remains understated. No vivid petals, no dazzling signals. Just two lineages brushing past each other in ancient landscapes, slowly learning to communicate, though neither fully realizes it yet. Once insects began visiting flowers with at least a semblance of regularity, the stage was set for a new evolutionary experiment, one in which visibility mattered. Not all flowers were equally successful in attracting insect partners. Some received more visits simply because they were easier to find. Others blended too well into the green tapestry around them and remained unnoticed, their pollen waiting in vain for a traveler who would never arrive. Slowly, almost reluctantly, evolution began sculpting flowers into signals. At first, the changes were faint. Imagine a world where flowers start to brighten just slightly, the way dawn nudges the horizon before sunrise. Petals that once mirrored the muted tones of surrounding leaves began to shift toward pale yellows or soft whites. These small changes helped insects discern them against a monochromatic background, even if only at close range. Visibility became an advantage, and advantages have a way of leaving marks across deep time. As insects responded to these subtly brighter blossoms, a feedback loop formed. Flowers that stood out even modestly were visited more often. Their pollen transferred more reliably. Their offspring produced more frequently. Meanwhile, flowers that remained too understated quietly dwindled. Evolution does not punish. It simply forgets those who fail to compete. In this era, subtlety wasn't always a winning strategy. A flower could remain modest, but modesty needed to be paired with luck, and luck is not something evolution guarantees. With increased reproductive success came increased experimentation. Petals began to diversify in shape and arrangement, not purely for aesthetics, but because different forms interacted with light in different ways. A slight curve could make a petal catch sunlight just right. A sharper edge could create a clean border against surrounding vegetation. Even the thickness of a petal affected how light passed through it, producing gentle variations in glow and intensity. Color chemistry also gained new purpose. Pigments that once functioned primarily as internal protectors now found themselves influencing external perception. Carotenoids added warm yellows and golds, giving flowers a soft radiance visible to wandering insects. Anthocyanins deepened into reds, purples, and blues in certain lineages, though these richer hues often served more than one function, helping flowers manage temperature, light stress, or attracting early insect specialists. Every pigment molecule had a job, but now part of that job included catching someone's eye. Contrast became invaluable. Flowers developed internal patterns, slightly darker centers, lighter rims, or faint lines leading toward pollen and nectar. These weren't yet the elaborate nectar guides of later evolutionary stages, but they were directional cues. An insect landing on a flower could follow these contrasts inward, guided almost unconsciously toward exactly where the plant wanted its visitor to go. These patterns improved efficiency for both participants. Insects spent less time searching, and flowers wasted less pollen. Some flowers began timing their displays. Petals would open and close with daylight, optimizing visibility when their pollinating guests were most active. The very act of unfolding petals in the morning created a dynamic signal, a small gesture that said, in botanical terms, "We're open for business." When night fell, petals might close again, conserving resources and protecting fragile reproductive parts. These rhythms were subtle forms of communication long before communication became explicit. The shapes of flowers diversified further as selection intensified. Bell-shaped blooms could capture and reflect light in a gentle, glowing pool. Flat-faced flowers provided broad, easy landing pads that caught the eye like small solar dishes scattered across meadows. Tubular forms, developing in certain groups, created stark silhouettes against foliage, elongated forms that hinted at specialized relationships still to come. Every variation contributed to the evolving visual language of flowers. Yet visibility wasn't just about bright hues or striking shapes. Scent and color began working together more tightly. A faint fragrance drifting through the air could guide insects from a distance, while color finalized the invitation up close. These multimodal signals strengthened pollination success and encouraged insects to return to the same floral types, promoting consistency that benefited both parties. As flowers became more noticeable, ecosystems transformed. Meadows that were once muted mosaics of green slowly gained speckles of brightness. Forest understories saw tiny points of reflected light, where blossoms caught slivers of sunshine filtering through leaves. Riverbanks shimmered with pale clusters that signaled opportunity to passing insects. The world did not burst into color all at once, but rather brightened like a painting gradually gaining layers. This chapter of floral evolution also introduced competition on a new front. Flowers now had to stand out not just against foliage, but against each other. Species sharing the same habitat found themselves in a gentle visual arms race. Some leaned toward brightness, others pursued contrast. Others diversified shapes to maintain distinct identities. No flower wanted to be mistaken for another, not out of vanity, but because precision mattered. A visitor distracted by a more noticeable neighbor meant missed chances. The refinement of color thus became a balancing act. Too much brightness could attract unwanted herbivores. Too little, and insects might overlook the bloom entirely. Flowers found themselves negotiating a middle ground between safety and visibility, learning to adjust color intensity based on environment and season. These delicate adjustments were guided by selection pressures that shifted across centuries and continents. Through all this, it's worth noting that flowers had no notion of being admired. Their brighter tones and clearer contrasts were not expressions of pride or desire for beauty. They were strategic adaptations, signals crafted through trial, error, and quiet persistence. If anything, evolution's message in this era was simple: being seen helps. And though subtlety has its charm, evolution discovered that in a world buzzing with insects, the wallflower approach could only go so far. A flower didn't need to shout, but it did need to speak. And so, for the first time, color began to function not as a byproduct, but as a language, one that would soon become more intricate, more vivid, and more essential than ever imagined. To understand this next chapter in the evolution of color, we must leave behind the world as humans see it and step cautiously and with great curiosity into the visual realm of insects. Their world is familiar yet transformed, painted not in the hues we recognize but in wavelengths our eyes were never built to detect. What looks to us like a simple yellow daisy or a plain white blossom might, through an insect's compound vision, burst with vivid ultraviolet patterns, directional arrows, landing pads, and hidden signals glowing like lanterns. As flowers and insects continued their ancient dialogue, subtle communication evolved into something far more deliberate. Flowers discovered that insects perceive wavelengths beyond human sight, particularly ultraviolet light. a region where many pigments absorb or reflect powerfully. Even without intent, early blossoms possessing slight UV reflectance differences enjoyed higher pollination success because insects navigated more accurately toward their resources. Evolution quickly learned to take advantage of this perceptual gap. What emerged was an astonishing expansion of floral patterning, designs invisible to mammals but radiant to six-legged visitors. These weren't flamboyant displays, they were navigational tools. Some flowers developed a bullseye pattern, a dark center surrounded by a UV reflective halo, guiding insects directly to pollen and nectar. Others formed intricate lines known as nectar guides, subtle streaks that pointed inward like runway lights. To humans, the petals remained unassuming. To bees, they were detailed maps. This shift represented a profound turning point. Color, once just a helpful signal, became an information system, a way for flowers to instruct insects with exquisite precision. The accuracy mattered. Fewer mistakes meant less wasted pollen, fewer misguided visitors, and more consistent reproductive success. Every successful pollination event reinforced the advantage of clear and visible signage. Ultraviolet patterns did not appear in a single form. Their diversity reflected the diversity of pollinators. Bees, for example, have trichromatic vision tuned to blue, green, and ultraviolet. Many flowers evolved patterns contrasting strongly in these wavelengths, dark centers against bright peripheries, or alternating bands resembling petals dipped in invisible paint. Flies, on the other hand, perceived UV differently, prompting flowers pollinated by them to develop broader, more diffuse reflectance zones. Even the textures of petals contributed to this hidden world of signals. Microscopic ridges and surface structures affected how light scattered across the petal. Insects could detect shifts in brightness and shimmer that humans would never notice. Some flowers gained a velvety appearance in ultraviolet, others a glossy sheen guiding insects across the petal surface like tiny road reflectors. For the insects, these variations were not artistic flourishes, but functional markers, enhancing grip, orientation, and movement. This silent communication extended beyond patterns. Some flowers oscillated their UV reflectance depending on temperature, hydration, or maturity, giving insects updated information about nectar availability or pollen readiness. A blossom low on resources could dim its UV guides, subtly discouraging visitors. One rich with nectar might brighten its patterns. In a sense, flowers developed a form of status indicator long before modern devices adopted the concept. For insects, responding to these cues became increasingly efficient. Bees could land, feed, and depart with practiced precision. They learned quickly, forming mental maps of which shapes and patterns correlated with worthwhile rewards. Their brains, though tiny, optimized routes between UV-friendly blossoms in ways that mystified early researchers. In turn, flowers adapted to these learned behaviors, refining their signals for maximum clarity. It was a partnership built not on affection, but on continually improving efficiency, an ancient optimization algorithm written in color. Meanwhile, the human perspective remained remarkably limited. To us, a flower's palette stops at the boundary of our visible spectrum. We see whites, yellows, reds, and blues. But what we call white often hides a complex visual message pulsing in ultraviolet. A seemingly plain blossom may be shouting directions in a language we cannot hear. The world, if glimpsed through insect eyes, would appear more luminous, more patterned, more structured. Meadows would be dotted not just with petals, but with neon markers and glowing pathways. Forest understories would shine with guiding streaks. The very air around flowers would feel charged with quiet signals. In this chapter of evolution, beauty was never the point. Precision was. Flowers honed their messages for eyes far smaller and far stranger than ours. Their signage served insects that could not offer critique or ranking or aesthetic appreciation. Flowers decorated themselves for an audience incapable of writing reviews, incapable even of conscious admiration, but perfectly capable of reading the cues that mattered. This partnership created an explosion of functional diversity. Some flowers concentrated UV reflectance at their edges, making petals appear like luminous halos. Others hid these signals until touched by sunlight, activating them only when insects were active. Certain species even developed UV-absorbing centers that contrasted sharply with reflective rims, forming an unmistakable landing target, one that human eyes miss entirely. The rise of ultraviolet signaling marked the moment flowers fully embraced the idea of communication. No longer merely visible, they became interpretable. No longer hoping to be noticed, they guided. And no longer responding only to light and environment, they responded to perception itself. This invisible world, woven across fields and forests, was one of the earliest examples of biological design guided by sensory experience rather than structural necessity. Evolution had begun tailoring traits specifically for another creature's viewpoint, and in doing so, it expanded color into a dimension far beyond human imagination, transforming petals into lanterns, guides, and maps across the ultraviolet landscape. Insect vision did not simply change how flowers looked. It changed how flowers thought, metaphorically speaking, about being seen. As flowers grew increasingly fluent in the language of visibility, they entered a new era, one shaped not only by insects, but by the physics of light itself and the peculiarities of animal perception. Color was no longer a simple beacon. It became a way for flowers to choose their partners, forming relationships that would last through epochs, climates, and shifting continents. To modern eyes, the diversity of floral color seems artistic. But behind every shade lies physics, ecology, and a touch of evolutionary matchmaking. The first major divide in this colorful story begins with the humble bee. Bees, with their trio of visual sensitivities tuned to blue, green, and ultraviolet, inhabit a perceptual world slightly shifted from ours. They cannot see red at all. It simply appears as a dull, unremarkable darkness. But blues and purples? Those glow like signals fired from nature's own lanterns. It's no surprise, then, that many flowers adopted these hues. Blue pigments are chemically demanding to produce. They require intricate molecular arrangements that reflect the higher energy wavelengths bees prefer. When a plant invests in a true blue or a deep violet, it is making a statement. I am courting bees. I expect frequent visits. Please land here responsibly. The reward system reinforces this. Flowers offering reliable nectar in these shades quickly gained loyal pollinators, while those with inconsistent rewards were politely avoided. Purple, often the result of layering anthocyanins with structural shifts in petal cells, became a near-universal favorite. Bees interpret these tones as vivid, high-contrast signals. For them, a purple bloom is like a neon sign advertising predictable benefits. In turn, bees visited these plants more efficiently and repeatedly, creating clear advantages that reinforced the evolution of blue and purple pigments. While bees shaped one end of the color spectrum, birds swooped in to influence another. Birds, especially hummingbirds in later evolutionary chapters, possess tetrachromatic vision extending well into the red spectrum. Where a bee sees darkness, a bird sees brilliance. A red flower, from a bird's perspective, stands apart from foliage like fire against dusk. Once birds became important pollinators, red rapidly became an evolutionary strategy. But these relationships weren't only about visual signals, they were equally shaped by physics. Red wavelengths are less scattered by atmospheric particles. They travel cleanly through humid air and forest understories, allowing birds to spot blossoms from greater distances than insects can. In tropical regions where bird pollination was especially advantageous, red became a favored hue. The flowers embraced it wholeheartedly, producing pigments like pelargonidin that deliver deep crimson tones. These reds weren't simply visually appealing, they were exclusive. Bees, unable to see red, tended to ignore these flowers. This gave birds unimpeded access, increasing pollination efficiency. It was a clever arrangement. By choosing red, flowers effectively filtered their audience. In a world where every visitor matters, this was a way of placing a velvet rope at the entrance. Birds only, please. But specialization came with costs. Blue flowers that relied on bees could falter if bee populations dwindled in a region. Red flowers dependent on birds faced risks during migration shifts or climatic changes. Still, the long-term stability of these partnerships made them worthwhile investments. Flowers that committed to a specific pollinator often evolved deeper structural adaptations. The precise curvature of petals to match a hummingbird's beak, or the thickness of a landing platform to support a heavy bumblebee. Color was merely the opening gesture. The architecture that followed sealed the relationship. Other colors found their own niches. Yellow flowers often appealed to both bees and certain beetles, providing a balance between visibility and broad accessibility. White flowers, especially those pollinated at dawn, dusk, or night, reflected light brilliantly in low illumination, making them favorites of moths and certain flies. For nocturnal pollinators, brightness mattered far more than hue. A pale bloom glowing in moonlight was essentially a lighthouse. Even scent and color began working as paired strategies across the spectrum. Blue and purple flowers tended to develop fragrances that bees could detect easily. Red flowers, targeting birds, often reduced scent production entirely. Most birds don't rely on smell. The absence of fragrance, combined with the exclusive visibility to red-tuned vision, made bird-pollinated flowers less attractive to insects that might drain nectar without effectively transferring pollen. Flowers, through trial and error, discovered a fundamental truth. No single color could attract everyone. Even if they wanted universal appeal, physics and biology would have disagreed. Light behaves differently at different wavelengths, and animals behave differently depending on what they can perceive. So flowers refined their strategies. They accepted that specialization was not limiting. It was efficient. Much like a restaurant choosing a cuisine, flowers learned that trying to cater to every visitor often results in pleasing no one particularly well. As millions of years passed, landscapes became mosaics of preference-driven color. Meadows shimmered with blue streaks where bees foraged. Tropical forests glowed with splashes of red where hummingbirds darted. Mountain valleys favored pale blossoms, tuned to the eyes of butterflies active at specific altitudes. Each ecosystem wrote its own palette, based on the physics of light, the creatures who lived there, and the structure of mutual benefit. This chapter of color evolution was not a chaotic explosion, but a careful sorting, flowers aligning themselves with the partners whose visits yielded the greatest reproductive success. The world did not simply become colorful, it became organized by color. And through all of this, flowers discovered a quietly comic lesson. No matter how lovely subtlety may be, it rarely wins the attention of multiple audiences. Better, they realized, to pick a partner, polish one's petals appropriately, and trust that in a world shaped by wavelength and eye structure, commitment is indeed an evolutionary virtue. When the work of pollination is finished, when petals have guided, scents have tempted, and visiting creatures have ferried pollen where it needs to go, the flower's role begins to change. It transitions from a beacon to a cradle. The delicate structures that once attracted attention now shift their purpose inward, protecting developing seeds. Petals often wilt away, retreating like actors slipping quietly off stage after their final lines. In their place comes the fruit, an invention that rewrote the relationship between plants and the animals that move through their world. At first glance, fruit might seem like an extravagant development for organisms that cannot move. But fruit is not indulgence. It is strategy, elegance crafted from patience and necessity. Its mission is simple: deliver seeds to distant, promising ground. Seeds alone can achieve this through wind or water, but these methods are unreliable. Animals, on the other hand, travel widely and frequently. If plants could entice them, gently persuade them to carry seeds inside their bodies or stuck to their fur, dispersal would become not only broader, but more predictable. This is where color re-enters the story, no longer for attracting pollinators, but for attracting diners. And so the fruit begins a remarkable transformation. It starts as green, almost invariably so. This green stage acts like camouflage, blending the developing seeds into their surroundings. Before they're ready, fruits want to remain unnoticed. Advertising too early would only result in loss. Animals, especially those with keen vision and persistent appetites, are remarkably adept at spotting anything that hints at nutrition. A fruit that signals before its seeds are mature risks surrendering its future to a hungry visitor. Only when the seeds reach readiness does the fruit begin to shift. Chlorophyll breaks down, making way for other pigments waiting quietly beneath the surface. Carotenoids that bring oranges and yellows, anthocyanins that create reds and purples, and deeper compounds that stain fruits a glossy black or blue. The shift is dramatic not because plants wish to impress, but because evolution finds honesty more reliable than trickery. A fruit that openly declares, "I am ready," attracts precisely the animals capable of helping its lineage spread. This vibrant transition is not just about color, it is about timing. The moment of ripeness is a delicate window. The seeds need to be mature enough to survive digestion or transport. But the fruit must not wait so long that it falls and rots on the ground. Animals have their own timing as well. Migrations, breeding seasons, and feeding cycles. Successful plants sync their color changes with these rhythms, producing fruits when animals are actively seeking high-energy food. It is a coordination honed by millions of years, an unspoken calendar shared across species. For frugivores, animals that specialize in eating fruit, color becomes a kind of shopping guide. Birds, with their excellent color vision, rely especially on reds and blacks. These hues stand out strongly against foliage, signaling nutritious pulp wrapped around seeds ready for dispersal. Many mammals, while less sensitive to red, detect contrasting brightness or scent changes associated with ripeness. Even reptiles and fish play roles in certain ecosystems, responding to fruit colors that align with their perceptual strengths. The honesty of this system cannot be overstated. Plants do not benefit from tricking diners with unripe fruit. An animal that bites into something sour, hard, or indigestible learns quickly. It avoids that plant species in the future. And avoidance is the one form of feedback a plant absolutely cannot afford. So evolution abandons deception. A ripe fruit tastes sweet, smells appealing, feels soft enough to eat, but firm enough to hold its seeds. Everything about it conveys readiness. Meanwhile, unripe fruit tastes bitter or tough, encouraging animals to leave it alone until its moment comes. And then, once eaten, fruits rely on animals to finish the job. Some seeds are designed to pass through digestive tracts unharmed, even strengthened. Others require partial digestion or chemical exposure to trigger germination. Certain seeds cling to fur or feathers via hooks or sticky coatings. A surprising number depend on animals caching them. Squirrels burying nuts, birds storing seeds, forgetting just enough of their hoarded treasures for forests to spread. Each fruit tells its own story through color. The blazing red of a tropical berry promises quick energy for birds darting between branches. The muted purple of temperate fruits invites mammals that forage at dawn and dusk. The deep black of a rainforest drupe absorbs light and signals maturity in dim understories. Even dry fruits that don't rely on color, pods, capsules, cones, benefit from contrasts when they split open, revealing pale seeds against darker husks. The evolution of fruit color also reshaped landscapes. Animals drawn to specific hues unintentionally sculpted plant distributions. A brightly colored fruit consumed by fast-moving birds could lead to seeds scattered across mountain slopes or remote islands. A heavier fruit eaten by ground mammals encouraged forests to expand along trails and water routes. What began as simple advertising turned into a shaping force, carving ecological patterns across continents. Still, for all its elegance, fruit evolution had its share of humorous byproducts. Some plants developed colors that were too appealing, attracting creatures that destroyed seeds rather than dispersing them. Others produced fruits so intensely pigmented that they risked over-ripening before anyone dared approach them. Evolution made adjustments. Tones softened, flavors recalibrated, protective chemicals measured carefully. It is not easy to find the perfect balance between irresistible and survivable. If evolution ever considered dishonesty, perhaps a bright, beautiful fruit with nothing to offer, it quickly abandoned the idea. The cost of misleading an animal outweighs any benefit. Plants do not thrive on broken trust. Instead, the system remains one of nature's purest examples of reliable communication. When a fruit turns vivid, it means it. Color here is not decoration. It is a promise, and promises are not given lightly. Fruits advertise what they genuinely offer, trusting that in the grand conversation between plants and animals, clarity will always serve them better than deceit. And so, each time a berry blushes red or a fig deepens to purple, it signals the same ancient truth. The seeds are ready, the world is waiting, and somewhere out there is a hungry traveler prepared to carry the future to new ground. As Earth cycles through its long climatic rhythms, ice ages advancing and retreating, warm intervals swelling across continents, rainfall patterns drifting like slow-moving tides, flowers face challenges far beyond attracting pollinators or enticing fruit eaters. Climate has a way of sweeping across landscapes with unhurried authority, reshaping ecosystems with every chill, thaw, drought, and deluge. And in these shifting conditions, color becomes more than a signal. It becomes a tool of endurance, a quiet mechanism that allows flowers to hold their ground or retreat gracefully when the world around them changes. During cooler periods, especially the great glacial cycles, vast stretches of land became harsher environments for delicate blossoms. Frost crept across regions once dominated by mild seasons. Shorter growing windows forced plants to rush their life cycles. In these climates, darker pigments offered advantages not tied to pollinator preference, but to physics. Darker hues absorb more sunlight, warming petals and reproductive organs in chilly air. This small thermal lift helped flowers maintain viable temperatures for pollen release and fertilization. Dark reds, deep purples, and even dusky blues provided microclimates on a petal scale, warming tiny pockets of space just enough to support the fragile processes of reproduction. Some alpine flowers today still demonstrate this strategy. They act like miniature solar collectors, soaking in sunlight and quietly boosting their internal temperatures. Their petals may appear dramatically pigmented, but beneath the color is a story of survival, not display. In colder epochs, such strategies allowed lineage after lineage to persist at the edges of ice. Conversely, during warm periods, some of them far warmer than anything humans have yet experienced. Brighter flowers often thrived. Light-colored petals reflect more sunlight, reducing heat stress. In intensely sunny environments, pale yellows, whites, and pastel shades helped protect delicate tissues from overheating. Even ultraviolet reflectance patterns sometimes shifted subtly to keep temperatures down, balancing visibility with thermoregulation. Climate demanded practicality. Flowers complied. But climate change did more than influence pigmentation. It reshaped the very architecture of blossoms. During cold intervals, many flowers grew smaller. Reduced size required fewer resources and minimized exposure to damaging frost. Smallness conserves heat, reduces water loss, and lowers the energetic cost of blooming. A prudent adaptation when seasons are short and nutrients scarce. Some lineages even retreated beneath snow cover or hugged the ground, using Earth's insulating properties for warmth. Their flowers remained close to their leaves, as if huddling for shelter. Warm periods told a different story. As forests expanded and competition increased, some flowers stretched upward, experimenting with height and structure. Others spread sideways, carpeting the ground in sweeping displays that responded to generous, stable climates. Color plays a role here too. In dense, warm forests, flowers sometimes developed richer contrasts to stand out in filtered light. In open, sun-soaked plains, softer colors diminished heat absorption, but maintained visibility in long distances. The landscape dictated the palette. There were also casualties. Some flowers disappeared entirely when climates shifted too quickly for adaptation. Their colors vanished with them. Tones that once brushed a valley or mountainside simply blinked out of existence. Evolution is patient, but climate can be abrupt. When glaciers advanced rapidly or droughts persisted beyond typical cycles, entire color schemes faded from the Earth's canvas. Their absence was not a failure. It was the natural ebb of ecological dynamics. Other species would rise, each painting new strokes across the land. Still, many flowers adapted quietly, adjusting their timing rather than their shape or color. They changed when they bloomed, aligning their schedules with new temperatures or rainfall patterns. A flower that once brightened early spring might shift toward late spring or early summer. Another might compress its blooming to a shorter, safer window. These changes were subtle, nearly invisible to the eye, yet critical to survival. Sometimes adaptation rests not in color or form, but in patience. Climate also influenced the distribution of pigments themselves. Some regions, particularly those shaped by strong sun or thin, high-altitude air, increased their production of protective molecules. These pigments deepened the visual richness of flowers even as they shielded them from ultraviolet radiation or oxidative stress. Elsewhere, in humid or overcast regions, flowers relied less on these protections, and paler blossoms often dominated. The world's floral palette became a reflection of atmospheric conditions, geological shifts, and seasonal rhythms. As environments reshaped themselves, so too did interactions with pollinators. Bees in cool climates leaned toward flowers capable of retaining warmth. Visiting a blossom that doubled as a heated rest stop was worth the trip. Birds in bright regions gravitated toward flowers whose colors stood out against sun-bleached backdrops. Butterflies in warm meadows favored blossoms that held stable temperatures under high midday light. These preferences reinforced floral color changes, creating a layered interplay between climate, physics, and partnership. Throughout Earth's climatic swings, flowers did not cling stubbornly to any particular aesthetic. They adapted with quiet versatility, reshaping their colors, forms, and timing as needed. Their relationship with climate was neither combative nor compliant. It was fluid, responsive, and deeply rooted in practicality. No matter how beautiful the resulting landscapes may have appeared, beauty was incidental. The true purpose of these adjustments lay in survival. Looking back across geological time, one can imagine entire eras where the world shifted from cool tones to warm tones, from muted petals to vibrant expanses, depending on what the climate allowed. These changes were not whimsical. They were strategic responses to a world that rarely stayed still. While fashion trends may come and go, climate does not ask permission before rewriting the rules. Flowers simply keep pace, adapting with quiet grace. And so each bloom, whether dark or bright, small or expansive, early or late, carries within it the imprint of ancient climate cycles. Their colors are not just signals to pollinators. They are memories of ice, warmth, storms, and sun. Through all of Earth's shifting moods, flowers continue to paint the landscape, adjusting their palette in ways that speak to both resilience and the silent artistry of survival. As flowering plants spread across continents, filling valleys, mountainsides, and open plains, something remarkable happened. The world became crowded. Not crowded in the sense of discomfort, but crowded in the sense of abundance, an explosion of botanical possibility. Meadows that once held a handful of floral species now brimmed with dozens, each one unfurling its petals into the sunlit air, each one vying for pollinators whose time and energy were not infinite. And in this bustling botanical marketplace, competition sharpened like a chisel. The earliest flowers lived in simpler neighborhoods, but now, in these diverse ecosystems, a single meadow could host multiple species blooming simultaneously. Bees, butterflies, beetles, flies, and birds passed overhead or moved through the foliage, and every flower hoped, quietly, imploringly, that it would not be skipped. Being overlooked was not an aesthetic tragedy. It was a biological one. Pollination is a numbers game, and fewer visits meant fewer seeds, fewer descendants, fewer chances to persist when seasons turned. Thus, evolution nudged flowers into a new phase, not toward beauty for its own sake, but toward distinction. Petals began to intensify their colors, as if adjusting the brightness on an ancient biological display. Blues deepened, yellows glowed more richly, purples thickened into velvety tones that seemed to pull gaze inward. Even whites became more radiant, reflecting sunlight with crisp clarity that stood out against green backgrounds. Flowers that once blended politely into their surroundings began assertively declaring, "Here I am." But color was only the opening bid. Patterns began to evolve with increasing complexity, each offering new ways to guide, entice, or convince pollinators. Some species adopted stark contrasts, bold markings that resembled eye spots, central discs that darkened sharply, radial lines that radiated outward like spokes of a tiny compass. These designs helped insects orient themselves quickly, saving precious seconds during each visit. Though flowers didn't intend to be artistic, their patterns often resembled brushstrokes from a painter experimenting freely with symmetry, rhythm, and flourish. Competition drove innovation in petal shape as well. Some flowers stretched their petals outward into broad platforms, the botanical equivalent of waving both arms to get attention. Others formed tubular entrances that required deliberate engagement, encouraging pollinators to commit their time. A few experimented with asymmetry, relying on unusual silhouettes to stand out against a sea of familiar forms. Each modification reflected subtle shifts in reproductive strategy. Where petals once existed simply to protect reproductive parts or support pollinator movement, they now doubled as visual advertisements. Scent, too, became part of this evolutionary theater. While the previous chapters explored its subtler guiding roles, in competitive ecosystems, scent acquired new significance. Flowers learned to strengthen their fragrances or refine them to better reach pollinators at distance or differentiate themselves among many blooming neighbors. Some produced sweet notes, others earthy or spicy tones, depending on the tastes of their targeted visitors. The air above these meadows carried a bouquet not merely of pleasant aromas, but of competing claims. Pollinators, for their part, were not passive participants in this story. They developed preferences based on reward consistency, ease of access, and memorability. In a meadow where every flower called out in color and scent, pollinators gravitated toward the most reliable and distinct signals. A bee that had rewarded success by visiting a certain hue or pattern began favoring those cues. Over time, flowers refined their signals to match these behavioral insights, creating a subtle dance of co-adaptation that played out at the level of both ecology and physiology. Some flowers took bold steps. Certain species developed dramatic color shifts in real time, altering hues as their nectar supply diminished or their reproductive parts matured. This was not deception, but efficiency. Pollinators learned that the richest rewards came from blossoms of a particular shade, and flowers broadcasted their availability through these changes. It reduced wasted effort for all involved. If one were to anthropomorphize, it would appear as though flowers had taken up the habit of flipping a neon sign from open to closed. Other species embraced extremity. Their petals grew saturated with pigments, their patterns sharpened into striking geometry. These intense visual strategies proved especially successful in sunny, open landscapes, where contrast made all the difference. Flowers that failed to stand out increasingly vanished from the ecological stage, leaving behind those that mastered attention without apology. Competition also encouraged temporal diversification. Flowers staggered their blooming periods to avoid overlap with too many neighbors. Early bloomers claimed the first wave of pollinators. Late bloomers seized those seeking resources after the rush. Even within a single species, individuals might bloom at slightly different times to hedge against unpredictable weather or pollinator variability. This subtle staggering was another form of visual spacemaking, temporal partitions in a crowded field. In some ecosystems, height became a competitive trait. Taller flowers rose above their rivals, catching breezes that carried their scent farther and providing visible cues to passing insects. Others remained low to the ground, relying on dense clusters to create a more concentrated visual impact. Where resources allowed, plants multiplied the number of flowers per stem, forming showy arrays that functioned like billboards promising abundant nectar. Not every flower embraced spectacle. Some relied on restraint, occupying niches where subtle signals remained effective. Shaded undergrowth, rocky ledges, isolated alpine zones. But in competitive meadows and forest clearings, subtlety became a luxury that many flowers could no longer afford. Evolution did not punish minimalism outright. Rather, it rewarded boldness where boldness paid off. This proliferation of strategies turned the landscape into a vibrant mosaic. Meadows became galleries of natural experimentation. Petals painted with gradients, fringed edges, or unexpected bursts of pigment. Forest margins glowed with blossoms, competing for narrow beams of sunlight. Hillsides shimmered with varieties that had learned, through generations, how best to declare their presence. And somewhere in the midst of this colorful rivalry, evolution learned a simple lesson. As flattering as modesty may be, it rarely secures abundant pollinators. In a crowded field, standing out is not vanity. It is survival dressed in bright, decisive hues. When humans enter the story of flowers, evolution encounters a new kind of partner, one that does not pollinate, does not glide from blossom to blossom on instinct, and certainly does not make decisions based on energy efficiency or nutrient gain. Humans arrive with an entirely different set of priorities: symbolism, beauty, curiosity, sentiment, and the irresistible urge to reshape nature into something that reflects their own desires. For flowers, this marks the beginning of an era where selection no longer whispers through slow environmental pressures. It bursts forth through deliberate hands, reshaping petals, colors, and fragrances at a pace nature alone never demanded. Early humans first noticed flowers not as botanical specimens, but as flashes of color breaking the monotony of green landscapes. Bright blossoms signaled edible plants, seasonal changes, or useful materials for dyes and medicine. Slowly, flowers became woven into human culture, not through coevolution, but through attention. A flower that caught someone's eye was plucked, carried, admired, and offered to another person. Beauty, which had never been the flower's goal, suddenly became a trait with social power. It was subtle at first. Humans simply gravitated toward certain flowers more than others. But preference has consequences, and over generations, plants near human settlements grew slightly differently. Seeds from the most appealing blooms were more likely to be gathered, transported, and planted, often unintentionally. Humans were not yet gardeners. They were wanderers with part-time horticultural tendencies, spreading floral diversity wherever they traveled. Eventually, intentional cultivation began. Humans selected plants with petals that leaned brighter, blooms that lasted longer, or scents that lingered in the evening air. Little by little, flowers found themselves shaped not by survival pressures, but by aesthetic opinions. A blossom that might once have been considered sufficiently vibrant by a bee suddenly found itself in a competition judged by human eyes, eyes capable of fixating on nuance, variation, and novelty. Flowers became, in a sense, collaborators in a new kind of mutualism. They offered beauty, and humans offered propagation far beyond what wind, water, or insects could achieve. Humans coaxed new colors from old pigments. Recessive genes that nature had left in quiet corners were encouraged to flourish. Mutations that produced unusual tones, lavenders, deep crimsons, pale creams, even bicolor petals were embraced and multiplied. Flowers that might have disappeared in natural selection due to producing inefficient signals for pollinators suddenly found themselves prized and protected. In gardens tended by human hands, a trait did not need to be useful, it needed to be loved. With cultivation came experimentation. Shapes stretched into unfamiliar forms. Some flowers doubled their layers of petals, creating lush, full blooms that resembled soft sculptures rather than reproductive structures. Others elongated, frilled, curled, or ruffled. Humans encouraged symmetry in some lineages and delightful asymmetry in others. If nature leaned toward practicality, humans leaned toward extravagance. Scent underwent its own renaissance. Flowers that produced faint fragrances experienced selective boosts from humans craving strong aromatic notes, sweet, spicy, citrusy, or musky. Fragrance became an art form. In some cases, flowers evolved scents richer than any pollinator would ever require, almost dramatic in their chemical overtures. A bee might find the intensity overwhelming, but humans found it enchanting. Some flowers, overwhelmed by the intensity of selective breeding, even lost their original pollinating partners and became dependent on gardeners for propagation. Their survival no longer hinged on natural interactions, but on human devotion. Color symbolism also played a significant role. Humans attached meaning to hues in ways no other creature does. Red came to represent passion, white, purity, yellow, joy, or sometimes sorrow, depending on culture and circumstance. These associations shaped cultivation. A flower with spiritual or cultural resonance was grown in abundance, sometimes in carefully maintained varieties that accentuated particular tones. Entire lineages expanded not for biological necessity, but because they became woven into rituals, ceremonies, and daily lives. As trade routes expanded, flowers traveled across continents. Some species that had once known only niche habitats found themselves thriving in distant lands, introduced intentionally or accidentally. Humans became global pollinators, dispersing seeds, swapping cultivars, sharing garden traditions, and mixing floral lineages at a speed evolution alone would never have achieved. A bloom that once relied on a single species of bee might suddenly find itself tended by gardeners thousands of miles away. Its traits amplified in directions it never encountered in the wild. Of course, not all human-driven selection was gentle. Some flowers were cultivated to extremes, brighter than necessary, larger than functional, more complex than pollinators could navigate. These ornamental marvels sometimes lost the traits that originally supported survival in the wild. Their stamina weakened, their reproductive mechanisms faltered, and their resilience diminished. Yet, in the sheltered world of gardens, this wasn't extinction. It was reinvention. Humans compensated with care, propagation, and enthusiasm. Flowers didn't need to endure harsh climates or compete in meadows. They needed to survive in pots, beds, and vases, winning human affection rather than ecological battles. In this new dynamic, flowers adapted, not genetically on their own terms, but through the hands of people who found joy in shaping petals and colors. Flowers learned, in a metaphorical sense, that pleasing everyone was unnecessary. Pleasing the humans who tended them was more than enough. And so the quiet evolutionary whispers of ancient landscapes became, through cultivation, a chorus of vivid hues and intricate forms. If flowers could reflect on this chapter, they might find it bewildering. They never asked to become symbols of love, grief, celebration, beauty, or ceremony. They never intended to be metaphors, decorations, or status markers. Yet here they are, thriving, traveling, diversifying, because humans saw something in them worth nurturing. And so flowers adapted again, not by natural pressures, but by sentiment, creativity, and cultural desire. They survived by accepting opinions they never asked for, and found themselves louder, brighter, and more cherished than evolution alone ever planned. As we arrive gently at the final chapter of this evolutionary journey, the landscape around us is no longer the quiet world of early pigments or the modest realm of tiny ancestral flowers. Instead, it is a mosaic of colors, an entire planet brushed with hues shaped by ancient necessity and modern complexity. Every blossom, no matter how simple or extravagant, stands as a record of what life has endured. Climate shifts, changing pollinators, geological upheavals, and the persistent, patient unfolding of time. The colors we see in flowers today are, in many ways, memories. Not memories in the conscious sense, of course, but biological remnants of decisions made across millions of generations. A streak of deep purple may carry the echo of an age when warmth was scarce, and darker pigments helped petals hold precious sunlight. A burst of gold may recall a lineage that found success by appealing to early pollinators attuned to warm wavelengths. Even a bloom that appears white to us might hum with ultraviolet patterns, preserving a communication method honed long before humans could imagine such hidden languages. When we look closely at a flower, we are witnessing not a static object, but the culmination of ancestral experiments. Each pigment molecule represents a response, sometimes clever, sometimes accidental, to challenges long forgotten by the world around it. The beauty we see is merely the visible layer of a deeply practical story. Evolution never aimed for aesthetics, it aimed for survival. Beauty is simply what happens when survival strategies accumulate with a certain elegance. This makes flowers both humble and profound. They decorate the edges of forests, the slopes of mountains, the margins of rivers, yet their presence is not ornamental. It is historical. A meadow in bloom is not a painting, it is an archive. Each petal contains countless revisions, like pages written and rewritten in the language of adaptation. Every shade of red or blue or yellow exists because something once needed it. Protection from heat, attraction of a pollinator, resilience against wind, a buffer for cold mornings or harsh light. The world's color palette is a living diary written molecule by molecule. Even chance plays its part. Mutations, those small, random shuffles in genetic code, have introduced countless variations into the floral spectrum. Most changes go unnoticed or vanish quickly, but some survive simply because they happened at the right moment under the right conditions. A rare pigment might persist because a new pollinator arrived unexpectedly. A subtle hue might thrive because it interacted well with the visual system of a wandering species. Some flowers owe their colors not to deliberate selection, but to fortunate coincidence, proving that improvisation is one of evolution's quiet strengths. And yet, change never stops. As climates continue to shift, as pollinator communities fluctuate, as ecosystems rearrange themselves in ceaseless motion, flowers respond. They retreat from regions that no longer support them and expand into new territories made viable by warming temperatures or altered rainfall. Their colors change accordingly, softening, darkening, brightening, or dividing into new patterns. The world is still teaching flowers what they must become, and flowers, ever patient students, continue to adapt. In this way, floral color becomes a record not of what once was, but of what is ongoing. Adaptation is never finished. Even now, petals are adjusting to new pressures, fragmented habitats, evolving insects, urban environments with unfamiliar rhythms of light. Some species shift colors to match nighttime pollinators taking over regions where daytime pollinators decline. Others alter pigment production in response to increased heat, using lighter tones to reflect sunlight. Evolution's workbench is never clean. There is always another shape to refine, another hue to test. And through all of this, flowers maintain a kind of quiet resilience. They are not defensive creatures. They do not hide behind armor or sharp edges. Their strength lies in flexibility, the capacity to alter chemistry, form, and color with a grace that belies the hard work beneath. They embody the idea that softness is not fragility, but a form of enduring adaptability. When humans encounter a flower, it is often framed by emotion, admiration, comfort, nostalgia, symbolism. Yet beneath these responses lies a story older and far larger than any cultural meaning. The colors that move us aesthetically were shaped by forces that cared nothing for beauty. forces that rewarded efficiency, precision, timing, resilience, and chance. The fact that these pragmatic strategies appear beautiful to our eyes is one of evolution's most delightful accidents. If evolution had a sense of humor, and perhaps it does in its own slow, geological way, it might smile at how its functional pigments became objects of human affection. It never set out to create art. It simply kept solving problems until, eventually, beauty happened. Flowers are reminders of this unintended artistry, complexity built from necessity, elegance born from patient adjustment. And so, as we leave this journey, imagine the world not as a static tableau of colorful blooms, but as a living, shifting manuscript. Each flower continues to write its chapter, shaping its palette according to whatever the present demands. Their colors, deep or pale, bold or hidden, remain markers of survival, persistence, and possibility. As the world changes, flowers will change with it. They will rewrite themselves slowly, thoughtfully, petal by petal, ensuring that the story of color continues not as an echo of the past, but as a promise of ongoing life.